Welcome. In this video, we will explore a powerful technique in calculus known as implicit differentiation. By the end of this lesson, you will be able to differentiate implicit relations and use this skill to find the gradient of a tangent at a specific point. First, let's understand what an implicit relation is. Most of the functions we've differentiated so far have been explicit functions, where y is written directly in terms of x. For example, y equals x squared plus 3x is an explicit function. We can easily find its derivative, dx, using standard rules. However, many important mathematical relationships are not so straightforward. They are defined implicitly. An implicit relation is an equation involving both x and y, where y is not necessarily isolated on one side. For instance, y cubed plus 3xi squared minus xy plus 11 equals 0 is an implicit relation. In such cases, it's often difficult, or even impossible, to rearrange the equation to express y as an explicit function of x. Yet we can still find the rate of change of y with respect to x or dx. Let's consider a classic example, the equation of a circle. The equation x squared plus y squared equals 4 represents a circle centered at the origin with a radius of 2. This is an implicit relation. It's also a relation, not a function, because for most x values, there are two corresponding y values. Visually, you can see that a vertical line can intersect the circle at 2 points, which violates the vertical line test for functions. One way to find dx for this circle is to split it into two explicit functions. We can rearrange the equation to get y squared equals 4 minus x squared, which gives us y equals plus or minus the square root of 4 minus x squared. The positive square root gives us the top half of the circle, and the negative square root gives us the bottom half. Now we can differentiate each part separately using the chain rule. For the top half, y equals 4 minus x squared to the power of 1/2. The derivative, dx, is 1/2 times 4 minus x squared to the power of negative 1/2 times the derivative of the inside, which is negative 2x. This simplifies to negative x over the square root of 4 minus x squared. Since y is the square root of 4 minus x squared, we can write this as negative x over y. For the bottom half, equals negative 4 minus x squared to the power of 1/2. The derivative is negative 1/2 times 4 minus x squared to the power of negative 1/2 times negative 2x. This simplifies to positive x over the square root of 4 minus x squared. Since y is negative the square root of 4 minus x squared, we can write this as x over negative y, which is also negative x over y. Notice that in both cases the derivative is the same. di bos dx equals negative x over y. This method works, but it's time-consuming and relies on us being able to rearrange the equation. What if we can't? This is where implicit differentiation becomes incredibly useful. It provides a more direct and powerful method. The core idea is to differentiate both sides of the implicit equation with respect to x, treating y as an unknown function of x. This means that whenever we differentiate a term involving y, we must apply the chain rule. The derivative of y with respect to x is simply dx. So, the derivative of y to the power of n with respect to x is n times y to the power of n minus 1 times di. This is a direct application of the chain rule, where the inside function is y. Let's resolve the circle example using this method. We start with our equation, x squared plus y squared equals 4. We differentiate both sides with respect to x. The derivative of x squared is 2x. The derivative of y squared with respect to x is 2e times dx by the chain rule. The derivative of the constant 4 is 0. Now our goal is to solve for dx. We treat it like any other variable. Subtracting 2x from both sides gives us 2y times dx equals negative 2x. Dividing by 2e, we get dx equals negative x over y. This is the same result we found earlier, but with much less effort. This demonstrates the power of implicit differentiation. We can find the derivative without ever having to solve for y explicitly. Let's work through a few more examples to solidify this concept. We'll start with some basic differentiation of terms involving y. First, let's find the derivative of 1 over y with respect to x. We can rewrite 1 over y as y to the power of negative 1. Using the chain rule, The derivative is negative 1 times y to the power of negative 2 times dai y. This simplifies to negative 1 over y squared times dai e. Next, let's try a term that requires the product rule. We need to find the derivative of x times y squared with respect to x. Here we have a product of two functions of x and y squared. Applying the product rule, we get the derivative of the first term, which is 1 times the second term, y squared, plus the first term x, times the derivative of the second term. The derivative of y squared is 2y times dx. So the final result is y squared plus 2xe times dx. Now let's combine these ideas to find dx for a more complex implicit equation. Consider the equation x plus x squared y plus y cubed equals 100. We differentiate each term with respect to x. The derivative of x is 1. The derivative of x squared y requires the product rule, giving us 2xi plus x squared dx. The derivative of y cubed is 3 squared dx, and the derivative of 100 is 0. Next, we group all terms containing dx on one side and all other terms on the other side. This gives us x squared plus 3y squared, all times dx equals negative 1 minus 2xi. Finally, we solve for dx by dividing. The derivative is negative 1 minus 2xe, all over x squared plus 3i squared. A common application of implicit differentiation is finding the gradient of the tangent to a curve at a specific point. When dealing with implicit relations, the derivative dx is usually expressed in terms of both x and y. Therefore, to find the gradient at a point, you need both its x and y coordinates. Let's find the gradient of the tangent to the curve x squared plus y cubed equals 5 at the point where x equals 2. First, we need to find the y-coordinate that corresponds to x equals 2. We substitute x equals 2 into the original equation. This gives us 2 squared plus y cubed equals 5, which simplifies to 4 plus y cubed equals 5. Subtracting 4, we get y cubed equals 1, so y must be 1. The point of tangency is 2, 1. Next, we find the general expression for the gradient, dx, using implicit differentiation. Differentiating both sides with respect to x, we get 2x plus 3i squared dx equals 0. Solving for dx, we find it equals negative 2x over 3y squared. Finally, we substitute the coordinates of our point, x equals 2 and y equals 1, into the derivative. The gradient is negative 2 times 2 divided by 3 times 1 squared, which equals negative 4 over 3. So, the gradient of the tangent at the point 2, 1 is negative 4, 3. Visually, you can see the curve x squared plus y cubed equals 5, the point 2, 1, and the tangent line with a gradient of negative 4, 3. Let's tackle a more advanced problem, which is typical of the IB/HL curriculum. This problem involves finding the second derivative, d2y dx2. We are given the relation x squared plus 2xe plus y squared equals 4. We need to find both the first and second derivatives. First, let's find the first derivative, dx. Differentiating each term with respect to x, we get 2x plus 2 times the product rule for xy plus 2y dx equals 0. This simplifies to 2x plus 2y plus 2x dix plus 2y dx equals 0. Grouping terms and solving for dx, we find that dx equals negative 1. Now for the second derivative. We differentiate the first derivative, dx equals negative 1, with respect to x. The derivative of a constant is always 0. So the second derivative, d2i dx2, is 0. This result might seem surprising. Let's investigate why. The original equation, x squared plus 2xe plus y squared equals 4, is a perfect square. It can be factored as the quantity x plus y squared equals 4. Taking the square root of both sides, we get x plus y equals plus or minus 2. This means the original relation is just two straight lines. Y equals negative x plus 2 and y equals negative x minus 2. Since both of these are straight lines with a constant gradient of negative 1, their second derivative is indeed z0. This example beautifully illustrates how implicit differentiation can reveal the true nature of a relation. Let's look at another HL-level problem involving a more complex implicit relation. We are given the curve y to the power of x times y minus x times y squared equals 1. We need to find d dx and the gradient of the tangent at x equals 0. First, let's find dx by differentiating the entire equation with respect to x. The first term, e to the x times y, requires the product rule. Its derivative is e to the x times y plus e to the x times dx. The second term, negative x times y squared, also requires the product rule. Its derivative is negative y squared minus 2xi times dx. The derivative of 1 is 0. Now we group the dx terms and solve for it. This gives us dx equals y squared minus e to the xy all over e to the x minus 2xi. Next, we need to find the gradient at x equals 0. We first find the corresponding y value by substituting x equals 0 into the original equation. This gives us e to the power of 0 times y minus 0 times y squared equals 1. Since e to the power of 0 is 1, this simplifies to y equals 1, so the point is 0, 1. Finally, we substitute x equals 0 and y equals 1 into our expression for dx. The gradient is 1 squared minus e to the power of 0 times 1, all over e to the power of 0 minus 2 times 0 times 1. This simplifies to 1 minus 1 over 1, which is 0. The gradient of the tangent at the point 0, 1 is 0. Let's conclude with a problem that combines implicit differentiation with the concept of perpendicular tangents. We have the relation sine x plus cosine y equals 0.5. We are given 2 points, P and Q, on the curve. P is on the y-axis, and the tangents at P and Q are perpendicular. We need to find the coordinates of Q. First, let's find the coordinates of P. Since P is on the y-axis, its x-coordinate is 0. Substituting x equals 0 into the equation, we get sine of 0 plus cosine y equals 0.5. Since sine of 0 is 0, we have cosine y equals 0.5. The principal value for y is pi over 3. So P is the point, 0, P3. Next, we find the gradient of the tangent at P. We need dx. Differentiating the equation implicitly, we get cosine x minus sine y dx equals 0. Solving for dx, we get cosine x over sine y. Now we substitute the coordinates of P, 0, pi 3, into the derivative. The gradient at P is cosine of 0 over sine of pi 3, which is 1 over root 3 over 2, or 2 over root 3. We are told the tangents at P and Q are perpendicular. This means the product of their gradients is negative 1. The gradient at Q, which we'll call MQ, is the negative reciprocal of the gradient at P. So MQ equals negative root 3 over 2. Now we have 2 conditions for point Q. It lies on the curve, and its gradient is negative root 3 over 2. We can set up a system of equations. From the gradient condition, we have cosine x over sine y equals negative root 3 over 2. From the curve equation, we have sine x plus cosine y equals 0.5. Solving this system requires some trigonometric manipulation. From the first equation, we can write cosine x equals negative root 3 over 2 times sine y. Substituting this into the second equation gives us negative root 3 over 2 sine y plus cosine y equals 0.5. This is an equation of the form a sine e plus b cosine e equals c. We can solve it by converting the left side into the form r cosine e plus alpha. After some work, we find that y equals 2 pi 3 as a solution. Finally, we find the x-coordinate of Q by substituting y equals 2p3 back into the original equation. Sin x plus cosine of 2p3 equals 0.5. Since cosine of 2p3 is negative 0.5, we have sine x minus 0.5 equals 0.5, which means sine x equals 1. The solution for x is p2. Therefore, the coordinates of Q are p2, 2 pi 3. Let's quickly recap what we've learned. We've seen that implicit differentiation is a powerful technique for finding the derivative dx when y is not explicitly defined as a function of x. The key is to differentiate both sides of the equation with respect to x, remembering to apply the chain rule to any term involving y. This means multiplying the derivative of the term by d, use product, quotient, and any other rules needed. We then proceed to make dx the subject of the equation. We also saw how to use this derivative to find the gradient of a tangent at a specific point, which requires knowing both the x and y coordinates of that point. Now, to help you master this topic, here are 5 practice questions in the style of the IBHL exam. Pause the video, work through them, and then check your solutions. Here is your first practice question. Find dx for the relation x cubed plus y cubed equals 6xy. Pause the video now and give it a try. Welcome back. Let's go through the solution. We differentiate both sides with respect to x. The derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared dx. The right side, 6xy, requires the product rule, giving us 6y plus 6x dx. Now we group the dx terms. We get 3y squared minus 6 all times da equals 6y minus 3x squared. Dividing, we find dx equals 6y minus 3x squared, all over 3y squared minus 6. We can simplify this by dividing the numerator and denominator by 3, giving us 2y minus x squared, all over y squared minus 2x. Here is your second practice question. Find the equation of the tangent to the curve x squared plus y squared equals 25 at the point 3, 4. Pause the video and solve this problem. Let's review the solution. First, we find dx. Differentiating the equation gives 2x plus 2y dx equals 0. Solving for dx, we get negative x over y. Next, we find the gradient at the point 3, 4 by substituting x equals 3 and y equals 4 into our derivative. The gradient is negative 3, 4. Finally, we use the point gradient form of a line. Y minus y1 equals m times x minus x1. Substituting our point and gradient, we get y minus 4 equals negative 3 4 times x minus 3. Rearranging this into the form y equals mx plus c, we get y equals negative 3/4 p plus 25 4. Here is your third practice question. Find the second derivative, d2 dx2, for the relation x squared plus y squared equals 25. Pause the video and work through this problem. Let's go through the solution. From the previous problem, we know the first derivative is dx equals negative x over y. To find the second derivative, we differentiate dx with respect to x. We must use the quotient rule. The derivative of the numerator, negative x, is negative 1. The derivative of the denominator, y, is li. Applying the quotient rule, we get negative y minus negative x times dx all over y squared. This simplifies to negative y plus x times dx all over y squared. Now here's the crucial step. The second derivative still contains the first derivative, ddx. We must substitute our expression for dx back into the equation. Substituting negative x over y for dx, we get negative y plus x times negative x over y all over y squared. This simplifies to negative y minus x squared over y all over y squared. To simplify further, we can multiply the numerator and denominator by y. This gives us negative y squared minus x squared, all over y cubed. Factoring out a negative sign, we get negative times the quantity x squared plus y squared, all over y cubed. Finally, we can use the original equation, x squared plus y squared equals 25, to simplify this even more. Substituting 25 for x squared plus y squared, we get the final answer. x2 equals negative 25 over y cubed. Here is your fourth practice question. Find the coordinates of all points on the curve x squared minus 3xi plus y squared equals 7, where the tangent is horizontal. Pause the video and solve this problem. Let's go through the solution. First, we find dx. Differentiating the equation gives 2x minus 3 times the product rule for xy, plus 2pi b dx equals 0. This simplifies to 2x minus 3 minus 3x di yak plus 2 d equals 0. Grouping terms and solving for di slash dx. We get di slash dx equals 3 minus 2x all over 2y minus 3x. A horizontal tangent has a gradient of 0. So we set di dx equal to 0. This means the numerator must be 0, so 3y minus 2x equals 0, which implies y equals 2 threes. Now we have a relationship between x and y for the points where the tangent is horizontal. We substitute this into the original equation to find the coordinates. Substituting y equals 2 and 3x into the original equation, we get x squared minus 3x times 2 by 3 dogs plus 2 3 dogs squared equals 7. This simplifies to x squared minus 2x squared plus 4 to 9x squared equals 7. Combining the x squared terms, we get negative 5 9 squared equals sin. Solving for x, we find x equals plus or minus 3 times the square root of negative 7 5. Since we cannot take the square root of a negative number, there are no real solutions for x. This means there are no points on this curve where the tangent is horizontal. Here is your final practice question. Find the exact gradient of the tangent to the curve arcsin of xy plus y equals 2 pi slash 3 at the point where y equals pi slash 2. Pause the video and solve this problem. Let's go through the solution. First, we find the x coordinate. Substituting y equals pi 2 into the original equation, we get arcsin of x times pi is 2 plus pi 2 equals 2 pi 3. Subtracting pi 2 from both sides, we get arcsin of x pi 2 equals pi 6. Taking the sine of both sides, we get x pi 2 equals sine of pi 6, which is 1/2 fahab. Solving for x, we find x equals 1 pi. The point is 1 pp2. Next, we find di dx by differentiating the equation implicitly. The derivative of arcsin of u is u prime over the square root of 1 minus u squared. Here u is xy, so u prime is y plus x di dec. The derivative of y is di dec. The derivative of 2 pi 3 is 0. This equation looks complicated, but we don't need to solve for di dx in general. We can substitute the coordinates of our point, x equals 1 pi and y equals pi slash 2, directly into this equation. The term xy becomes 1/2. So we have pi 2 plus 1 pi d dx all over the square root of 1 minus 1 quadras plus dx equals 0, 0. The square root simplifies to root 3 over 2. Multiplying by root 3 over 2, we get pi over root 3 plus 2 over pi. Root 3 d slash dx plus diagonal plus di slash x equals 0. Factoring out di slash x, we get di slash dx times the quantity 1 plus 2 over pi root 3 equals negative pi over root 3. Solving for di slash de, we get negative pi over root 3, all divided by 1 plus 2 over pi root 3. Multiplying the numerator and denominator by pi root 3, we get the exact gradient, negative pi squared over pi root 3 plus 2. That concludes our lesson on implicit differentiation. We've covered the fundamental concepts, worked through several examples, and tackled some challenging IB-style problems. Remember, the key is to treat y as a function of x and apply the chain rule whenever you differentiate a term involving y. With practice, this technique will become second nature. Thank you for watching.